Now that we've gone through the physical anatomy, it's time to figure out the physiology. What are the actual mechanisms of breathing? How do you breathe? Because if you think it's just breathe in, breathe out, it's a bit more than that. So first off, there's two main phases. There's the inspiration and the expiration phase. Inspiration, you breathe in. The air is entering your lungs. Expiration is you're breathing out. Air is leaving the lungs. Now, that sounds simple enough, but we'll have to get more into this later, not right this second, but really the way your body thinks of it is breathe in and then don't breathe in. Breathe in and basically inhibit breathing in. So your exhalation is actually your body trying to inhibit the inhalation, just stopping what's going on. But we'll come back to that a little more later. For now, let's work about some of the basic pressures and go from there. So first off is atmospheric pressure. Now notice P subscript ATM, that's atmospheric pressure. Atmospheric pressure is what is the pressure around you that's pushing on your body. So at sea level, it's 760 millimeters of mercury. Hg is mercury. Now, if you're not dead at sea level, it starts to decrease as you get higher. So maybe if you're just a little bit above that, it's 759 millimeters mercury or 758 millimeters, whatever it is. We're going to assume 760 millimeters of mercury at sea level just for simplicity. Now, when you start talking about respiratory pressures, a lot of times they'll say it's -3 or -4 or +2. Those are in relation to the atmospheric pressure. Because in reality, we're not talking about pressure of 2. It's 2 in relation to the 760. So for example, a negative respiratory pressure. Let's say we had -2. -2 respiratory pressure. That would be -2 in comparison to the 760, which means really that's 758 millimeters of mercury. Just -2 is a lot easier. If it's positive, well, that just means you're going above it. +3 respiratory pressure. That's 763. Just you're 3 above atmospheric. And a 0 respiratory pressure means you're exactly equal to the atmospheric pressure. So just a little idea of how these are relative terms, not absolute numbers. It's in relation to the atmospheric. Then we have also the intrapulmonary pressure. Now the intrapulmonary pressure, which is P subscript PUL, intrapulmonary pressure, that is going to be the pressure inside the alveoli. The pressure inside your lungs, basically. Now that will fluctuate as you breathe, because the way your air goes in and goes out of your lungs is based on pressure gradients. So by changing the pressure inside the alveoli, changing the pressure of this intrapulmonary, you help the air flow in or flow out. Now eventually, this always reaches equilibrium. The intrapulmonary pressure will always equilibrate with atmospheric pressure. Because when you breathe in and pause, that pause inhalation is equaling the pressures out. When you breathe out, when you pause, that end of the exhalation, that's the equilibration between atmospheric pressure and the intrapulmonary pressure. So it constantly changes, but it always comes back to equilibrium, to equaling out to atmospheric. Now there's also an intrapleural pressure. Intrapleural, or P subscript IP, that intrapleural pressure is looking at the pressure inside the pleural cavity. Now that's going to be important because that pressure inside the pleural cavity better always be negative in relation to the atmospheric, in relation to the intrapulmonary. Because that pressure, while it will fluctuate, has to remain negative because it helps to keep the lungs fully seated on the thoracic cage. So that negative pressure almost creates a little suction right there to keep the lungs out on the thoracic cage. If that ever was not a negative number, that lung would collapse. So this whole idea of this negative intrapleural pressure, caused by two inward forces and one outward force. We'll get to that one in a second. The two inward forces, elastic recoil of lungs and surface tension of the alveolar fluid. Let's start with the elastic recoil. Your lungs naturally want to collapse to a smaller size. Therefore, they're always trying to pull down. So this inward force is the lungs trying to become smaller. You don't want that because you need to keep them expanded so air can flow in. Secondly, surface tension. We mentioned that the intrapleural pressure is negative, but that intrapleural space between the visceral and parietal, that's fluid filled, remember. There's surface tension. The fluid doesn't want to pull away. I'm not sure if you've ever had two pieces of glass together or two pieces of plastic together, and there's moisture in between. Just simply trying to pick it up doesn't work. You gotta slide them off each other because there's too much surface tension just to simply pick up the two sheets of glass, or two sheets of plastic, if there's any fluid between. Now, those are the inward forces. There is an outward force as well. The outward force is looking at the elasticity of the chest wall. That's going outward, trying to pull out away from it. So all of these together are what combine to make the negative intrapleural pressure. So here's what we're looking at. If you have P subscript IP, so the pressure of the intrapleural equaling P subscript PUL, the pressure of the pulmonary, so looking at the inside of the lungs, or if it's atmospheric, either way, then your lungs collapse. Done. They cannot be equal. You have to have that negative. So what we're looking at is what's called a transpulmonary pressure. Now this transpulmonary pressure is looking at the pulmonary and the intrapleural pressures. So you can see it's P subscript PUL minus P subscript IP. That's your transpulmonary pressure. That's what keeps the airways open, not just the alveoli, but the alveolar ducts, the respiratory bronchioles, all those small pieces. If not, they simply collapse on down. So we're looking at this negative transpulmonary pressure. And it can change. It doesn't have to always be the same, but it must be a negative value. The greater the transpulmonary pressure, so instead of -4, maybe it's -5, -6, -7. So the more negative, the larger the difference, the larger the lungs are. The way you can think about it is if these lungs are trying to recoil smaller, but you stretch them out even more, they have even more force wanting to recoil. Think about a balloon. If you take a balloon and blow it up just a little bit, does it really shrink that much? No. But blow it up almost to its max, that's going to very quickly and have vigorous force trying to collapse back down. That's your lungs. The more they're expanded, the more force they want to collapse with, which means you have to have a larger difference, so a larger negative transpulmonary pressure. So from a visual standpoint, here's what we're looking at. Now I'm going to throw this up full screen just so you can see the different pieces and nuances. So first off, we're going to have this intra-alveolar pressure or the intrapulmonary pressure. Notice that intrapulmonary pressure is 760 millimeters of mercury. Think atmospheric at sea level. Then you have what's referred to as the intrapleural pressure. Now the intrapleural pressure is 756 millimeters of mercury. That's what's in between the visceral and parietal membranes. So you notice there's a 4 millimeter of mercury difference. And that's where the transpulmonary pressure comes from. 760 millimeters of mercury minus 756 millimeters of mercury. -4 millimeters of mercury is your transpulmonary pressure. Now, if the lungs expanded beyond that, they got even bigger, well, then at that point, you can still have the 760 millimeters of mercury pressure for the intrapulmonary. But the intrapleural, because the lungs want to recoil more, would be lower. It could be 755 or 754. So as the lungs get bigger, that intrapleural pressure drops because there's more of that internal force pulling, trying to collapse the lungs, which means then the negative transpulmonary becomes more negative. -5, -6, -7. So looking at these different values, it's trying to tell you the functionality of the lungs. Looking at, is everything working properly? What pressure looking at? How's it all working together? So we have to keep an idea of how these pressures are all working together. Now, one imbalance is the idea of a lung collapse. If you notice, atelectasis, that is a collapsed lung. It can happen for different reasons. One reason is the alveoli or the bronchioles getting clogged. If you have enough of these respiratory bronchioles getting clogged up, that means the alveoli can't get any air and they start to collapse. As they collapse, more and more collapse, eventually there's enough internal force just to pull in. Lung collapses down. If a lung collapses, you really can't use it to breathe. You're only breathing with a non-collapsed lung. Other one is pneumothorax. That's where if you had a damage, maybe a stab or a cut or a fractured rib, that punctures through the pleura. So you puncture the parietal pleura. That means that thin pleural cavity now is exposed to the outside environment. The pressure from the outside can get in there. You cannot maintain your negative transpulmonary pressure. It's not a sealed environment. That's why for a collapsed lung, to try to uncollapse it, there needs to be a solid airtight seal removing the excess fluid or air along the lung to open back up again, and then maintaining that seal afterwards. Because if that seal isn't maintained, then the air goes back in, the whole process reverts. So a little about the physiology of the pressures inside the lungs and how those pressures relate to keeping the lungs expanded.